You know what DAC stands for? It is digital to analog converter. Okay. So it's a device which is widely used for converting digital pulses to analog signals. So for DAC interface, what input you are going to provide and what is the output you are going to get, that is what the main concept you need to understand. Okay. So DAC is actually a device which is widely used for converting digital pulses to analog voltage. So this is the DAC interface component which you are going to use in your lab. Okay. Coming to the interface diagram of DAC. Okay. So first we'll discuss the interface diagram of DAC. After that, we'll look into different types of problems which you can expect on DAC interface. Okay. So this is the interface diagram you have to write if it is asked to explain with a neat diagram DAC interface. Okay. So what this DAC interface consists of is the DAC chip, okay, op amp and the voltage converter. So these are the major components you find in the DAC interface. And you are going to interface LPC2148 microcontroller to this DAC component. So DAC consists of these major components, that is DAC chip or DAC IC, op amp and voltage converter. And you can see here the number of data input bits. So that actually decides the resolution of DAC. So that means if it were to be n digital input pins for DAC, in that case that DAC is capable of generating 2 to the power of n analog voltage levels. So based on number of digital inputs available for DAC, you can tell how many levels of voltage that DAC can generate. Okay. So if it were to be n digital input pins, then there are 2 to the power of n analog voltage levels. So the DAC IC what we are using in the lab, so that is having 8 input pins, so that it provides 2 to the power of n, that is 2 raised to 8 means 256 analog voltage levels it can generate. So that is 0 to 255 is the range of analog voltages this DAC component can generate. So that is what the IC are using for interfacing with LPC2148 microcontroller. So remember, it is having 8 input pins which provides 256 analog voltage level. Okay. And you can observe the output of DAC. It is connected to an op amp, and in turn, that is op amp with this feedback resistor, and the final output that is connected to the CRO for displaying the waveform. So here, while interfacing this DAC to LPC2148 microcontroller, you will be connecting CRO so that whatever the analog voltage that is generated from this DAC interface, so that is displayed on the CRO through the waveform. Okay, so this is what you are going to observe in this DAC interface. So what are all the points you need to remember with respect to DAC interface? So what it consists of, that is the DAC chip, op amp and voltage converter. How many data input bits are available in DAC, that decides the resolution of DAC, meaning n digital inputs if they are available for DAC. In that case, it is capable of generating 2 raised to n analog voltage levels. Okay. And coming to the DAC IC which you are using in the lab, it is having 8 input pins. So that's why 256 analog voltage levels it can generate. And coming to the connection, DAC IC is connected to the op amp with the feedback resistor, and output of this is connected to the CRO to see the waveform. Okay. As I told, 0 to 255 is the range of digital values you are having. So here we shall just see for sending the digital input, what value you are going to send, through which port pin you are going to send out the values. So that we are going to discuss. And after that, what digital value you are going to send for corresponding voltage level. So this is what we are going to discuss in the coming slide. Okay. Just see here, the output voltage of plus 5 volts, it is obtained from DAC when the digital input is FFH, and output voltage will be 0 volts when the digital input is 00. So that means using this DAC, this is what the analog voltage we can get, that is 0 to 5 volts. And what digital value corresponds to these analog voltages? It is 00H to FFH. The digital values 00H to FFH, it corresponds to the analog voltage 0 to 5 volts. So if you are sending 00H, the digital input, so you can see in this interface diagram, So we are going to provide the digital input, and through which port this digital input is given. It is port 1. So for DAC interface, it is port 1 of LPC2148 microcontroller that is used for sending out the digital input. We are going to send some digital value through port 1. Pins are port 1.16 to port 1.23. Through these pins, digital values are sent out. And using this DAC, that digital value is converted to corresponding analog voltage. Okay. So here, if you are sending the digital value 00H, what is the analog voltage that is generated? It is 0 volts. If you are sending the maximum value, that is FFH. So in that case, what is the analog voltage that is generated? It is 5 volts. So what you have to remember is the digital value 00H to FFH, they correspond to the analog voltage. It is 0 to 5 volts. As I just mentioned, in DAC interface, port P1, it is used as an output port, and whatever the 8-bit digital data you want to send out, that is sent out through port 116 to port 123 of the by LPC2148 microcontroller. So those are the points you need to remember with respect to the DAC interface. Coming to the display of sine waveform. So if you want to display sine waveform on the CRO, then what is the digital formula you have to use for generating the digital values or the discrete values? So for that, this is the formula you are going to use. See, the digital formula used to get the values for positive cycle of the sine waveform. It is 127 sine theta plus 127. Why it is plus 127 is, here we are going to take the reference voltage for displaying the sine waveform is 2.5 volts. So just see the sine waveform. So this is the positive cycle and this is the negative cycle. So how actually are going to display the sine waveform on the CRO is, you need to sample this waveform. That means you need to find out discrete values. So those discrete values you are going to send to the DAC interface, so that corresponding voltage level you are going to see in the CRO. Okay. So here you need to decide how many samplings you require. Say, for example, you want to compute 30 samplings for displaying the positive cycle. Then this is positive cycle means it is 180 degree. So 180 by 30 means you will get 6 degree. So in 6-degree increment, you have to find out the digital value by replacing theta with say sine 0, then sine 6 degree, sine 12 degree, and so on. So each time you are going to increment this angle by 6, and you are going to find out the digital value or the discrete value using this formula, that is 127 sine theta plus 127. Okay, so why it is plus 127 is 2.5 volt. So analog voltage 2.5, it corresponds to the digital value 127. So 0 volts means it is 00H digital value, plus 5 volt means it is FFH the digital value. Okay. So it is 2.5 volt. So if it were to be the reference line as 2.5 volts, then it is 127 or 7 FH the digital value. Okay. So here, since we are starting from this 2.5 volt for displaying the sine waveform, it is plus 127 the value in this formula, that is 127 sine theta. Why it is plus 127 is, since the reference voltage we are considering is 2.5 volts for displaying this sine waveform. So how actually we are going to display the sine waveform? For that you need to decide the number of samplings. If you decide 30 samplings for displaying the positive cycle of the sine waveform, so then just divide 180 by 30. What you are going to get is, it is 6 degree. So how actually are going to find out the discrete values? Just by increment the angle by 6 degree in that formula, so that you will get the discrete values. The rest, say for example, 127 sine 0 plus 127 will result in 127. So 127 sine 6 degree plus 127, it result in 140, and so on. So in the next value, how we are computing, it is 127 sine 12 degree plus 127, and so on. You are rounding off the value. It is not the exact value. You will get some fractional value. You are rounding it off to next higher or lower value, and you are finding out the digital value. And it is not that you need to calculate for complete 180 degree the values. If you just calculate for 90 degree till sine 90, if you just compute the values, And if the same values, whatever you have computed from sine 0 till sine 90, the same values if you just write in the reverse order, so that will be the value for rest half. Okay, so this is pi by 2. What you are going to do is you are trying to find out the discrete values for positive cycle. So if we just calculate till sine 90, that is sufficient. So same value if you just write in reverse order, so that will be the values computed for this half of the positive cycle. So this is how we are going to find out the discrete values for the positive cycle. To get the negative cycle, you need to take the 2's complement of whatever the values you have computed for positive cycle. Okay, that will invert the waveform. Okay, so that you'll get the negative cycle. So this is how we are finding out the discrete values for displaying the sine waveform. So what is the digital formula you have to remember? It is 127 sine theta plus 127. Okay, since we are taking the reference voltage as 2.5 volts, so it is plus 127 here. So 127, it corresponds to 2.5 volts analog voltage. Okay, and it is dependent on you how many samplings you want to do for generating the sine waveform. If you are going for 60 samplings, then 60 values you need to send out the digital value, so that you will get the still more clearer waveform. The more the sampling, more clearer the waveform will be. So here we have taken 30 samplings. We are deciding for 30 samplings. So since we need to find out the discrete values for generating the positive cycle, it is 180 by 30. So this is 0, this is pi by 2, and this is pi. So 0 to pi, that is the pause for positive cycle. I need to find out the discrete values. So 180 by 30, it results in 6 degree. Just have a 6 degree increment in this formula and try to find out the discrete values. And these values we are going to initialize in the memory, and we'll be sending out these digital values to the DAC interface, so that corresponding analog voltage will be generated. Okay, so that it displays this positive waveform. Once this is done, to display the negative waveform, you have to take the 2's complement of whatever the 30 values you have you have computed. So that values 2's complement you have to find out, and that has to be sent out to the DAC interface, so that corresponding analog voltage will be displayed, and you can see the waveform in the CRO. So this is what you need to do for generating sine waveform. Okay, so as I told, more the sampling you are doing, more clearer the waveform will be. And this is not just exact value we are sending, we are rounding off the value. Once you get sine 6 degree, sine 12 degree, once you compute, it may be some fractional value, will be just converting it into whole number, and that value we are going to initialize in the memory. Okay, once we discuss the the syllabus program with respect to the sine waveform, you'll understand how actually we are going to initialize this discrete values in the memory. Okay, so this is about generating sine waveform using DAC interface, the digital formula to be used, how to do the sampling, how actually you are going to calculate the discrete values to display the positive and negative cycle of the sine waveform. Okay, so now coming to this is what I've already explained. Now we shall see one by one the different waveforms that we can generate. So this is actually the lab syllabus program, fifth program of your lab syllabus in part B. That is to generate a square and triangular waveform using DAC interface. Okay. So this is the square waveform which you have to generate. Just observe how actually the square waveform can be generated using DAC interface. So 0 volts. So if you want to get 0 voltage, it is 00H, the digital value you have to send out. And if you want to get 5 volts, you need to send out the digital value 255. This is in decimal. 0 to 255, it is decimal. 00H to FFH, it is in hexadecimal, the digital value. Here, what you have to do is you need to send 255. 255, we are going to send out FFH, the digital value, and you'll introduce some delay, so that it stays at this reference voltage, that is 5 volts. So after that you are going to send out the voltage 0. Okay, that is 00H digital value will send, and for some period of time you are going to introduce you are going to stay in that voltage level, so that it displays the square waveform. See, whatever the delay you have used for this T on, same delay you are going to use for T off. Okay, so that it displays the square waveform. So just see here what logic you are going to use in your program for displaying the sine waveform. You are going to send out FFH and you'll introduce some delay, and then you'll be sending 00H, the digital value, so that 0 volt reference line is got. Okay, and you are going to stay in that reference line for some period of time. So whatever the delay you have used for T on, same delay you are going to use for T off, so that it will be 50% duty cycle. That is, it will be the same waveform, that is the same width for T on and T off you are going to get, so that it displays the square waveform. So this is what the simple logic you are using. Just send FFH, introduce some delay, send 00H, introduce the same amount of delay. So this process, if you repeat for some fixed number of times, so it goes for displaying the square waveform. So coming to the triangular waveform, so I'm actually going to display this triangular waveform. Just see here, starting from 0 volts, you need to keep on incrementing the value. You need to find the discrete values, and that value will be sending out to the DAC interface till what value you'll be sending, till FFH, so that the maximum voltage of 5 volts is got. So after that you'll be decrementing, go on decrementing the value and until it reaches 0. Once it reaches 0, you repeat the process. So two loops we are going to use here for triangular waveform. One, the increment loop for increasing the value starting from 00H to FFH, and then another loop we are using is the decrement loop. So from FFH we need to just go on decrementing the value till it reaches 0. So one increment, one decrement loop we are going to write for displaying this triangular waveform. So 0 to 5 is the voltage range. So we need to display this triangular waveform. How we are doing it? Take the loop control variable I, initialize it to the digital value 0, and send that value through port 1. So port 1 dot 16 to port 1 dot 23. So through these pins only you have to send out the output, whether is a digital value, to the DAC interface. And after that you increment the I value. You send the next value again through port 1. This process will repeat until 255. After that we'll decrement the value and we'll be keep on sending the values until 0. So if you just enclose it within an infinite loop, it just keeps on displaying this triangular waveform. In our lab syllabus, the fifth program what we are having, it is to display both square and triangular waveform. So for that what we'll do is, for some period of time we'll display square waveform. After that we are going to display triangular. So alternately we'll be displaying square waveform and triangular waveform. So how actually it is done through the code, we'll see here. See, this is the first program under DAC interface we are discussing. Develop an embedded C program to generate square and triangular waveforms using DAC interface. Just the first step is you need to include the header file lpc214x.h. After that, this is the delay routine, which is common for all the interfacing programs wherever delay is required. Okay, nested looping construct you are having within this delay routine. Coming to the main function, here we are going to declare the variables required. I and j are the variables we are using here. Coming to the configuration of the registers in LPC2148 microcontroller, it is pin select 2 register we are using. Since port 1 is to be configured as GPIO port, we are going to initialize this pin select 2 register with 0. So next we need to configure IO dir register. You know that port 1 is used as an output port. So that's why port 1.16 to port 1.23. So these 8 pins I need to configure as output port pins. So for that purpose, this is what the value you are going to load to IODIR1 register. See, IODIR1 equals 0x00FF followed by that 4 zeros. So what happens once this is executed? It sets port 1.16 to port 1.23 as output port pins. Okay. After configuring the registers, next step is we need to display the square and triangular waveform. So this process we have to repeat infinitely. So that's why infinite while loop we have written. Within this, as I told, for some period of time we'll display square waveform, and after that we are going to display triangular. So alternately we'll be doing this infinitely. That is, we are going to display square and triangular waveform. See, for displaying the square waveform, this is what the for loop I'm using. For I equals to 0, I less than 1000, I plus plus. So within this, as you know that, what are the two voltage values we need to send out for displaying square waveform? It is FFH, the maximum voltage, and 00H for the 0 volts, correct? So that's these values we are going to send out. So if you want to send all ones, if you want to set the port pins with value logic 1, you need to write to IO set register, So IO set 1 is equal to 0x00FF followed by 4 zeros. What happens if you execute this? So we are going to send out through port 1.16 to port 1.21 value logic 1. So this is what we are going to send out. We'll introduce some delay, say delay of 20. After that, we need to send 0 volt. So for that, it is same value we are going to write FFH. Okay, to at which bit positions you are going to write FFH. It is P1.16 to P1.23. The writing of 1 to IO clear register is nothing but sending out logic 0. You know that. So writing 1 to IO set register, meaning you are sending logic 1 through that a particular port pins. Correct? So this is what we are doing here. And the same amount of delay you are introducing. Remember, it is the same amount of delay you have to introduce since it is square waveform you are trying to generate. Just see this this for loop for displaying square waveform. This is a simple logic you are writing. For I equals to 0, I less than 1000, I plus plus. So this is the period for which we are going to display the square waveform. So when you execute it practically, you'll come to know for what value you need to run the for loop. If it is too fast, it is displaying the square and triangular alternately. You can increase this increment loop. Okay. But since it's already tested, if you run the for the loop control variable for this value 0 till 1000, it is sufficient. You can see the square waveform. After completion of this for loop, you can go for seeing the triangular waveform. So like this, alternately, it keeps on displaying square and triangular waveform. So what you are seeing in this slide is the code for displaying square waveform. So this is the for loop header we have written. And within the for loop, what are the statements you are going to write? Send out FFH through port 1. And for that, we are going to, since it is all ones we have to send, we are writing to the IO set 1 register, introduce delay, then send out FFH again to IO clear register, so that logic 0 is sent out through these port pins, port 1.16 to port 1.23. Then introduce the same amount of delay. Just observe the delay whatever you have used for that is the T on, the same delay you have to use for T off. If you make change here, it becomes a rectangular waveform. So that is the only change compared to square waveform and rectangular waveform. Okay, so this is about square waveform. Coming to triangular waveform, see, this is the period for which we are trying to display the triangular waveform. For that, this is the for loop we have written. For I equals to 0, I less than 1000, I plus plus. So now here we need to increment. I told two loops we are going to write, one increment loop, one decrement loop. So starting from 0 volt till 5 volt we have to display, and after that 5 volts to 0. So for that, you know what digital value corresponds to the analog voltage 0 to 5. It is 0 to 255. You have to run the loop. See, the inner loop control variable, just see used is j equals to 0, j less than 255, j plus plus. So this is the for loop header we have written, and we have to send out at which pins we have to send out the data. It is port 1.16 to port 1.23. So we need to left shift 16 times the value held in j, and that we have to send out through IO pin register. So this is what the statement you are writing. IO pin 1 is equal to j left shifted 16 times. So what this will do is it displays uh, this half of the triangle. So till starting from 0 till 254 it displays. 254 means it is near to 5 volts. Okay, 254 digital value I have written, and it's not the analog voltage I have written. So 00H or decimal 0 to 254. So this is the increment loop what we have written. So if you are writing a decrement loop, that is j equals to 255. So till 255 we will display, then j greater than 0, j minus minus. It is the same statement. IO pin 1 is equal to j left shifted 16 times. So that a decrement loop is executed and it displays the rest part of the triangular waveform. See, 0 to 255, then 255 to 0. If you repeat this for fixed number of times, it just displays this triangular waveform. Okay, for some fixed number of times, it is not infinitely we are displaying triangular waveform. See, the loop we have taken is I equals to 0, I less than 2000. Only for this much delay we are trying to display this triangular waveform. This is the code for displaying a triangular waveform. For how much period you want to display the triangular waveform, that is controlled using this outer loop. So this we have actually enclosed within an infinite loop. Just here while one we have written, so for some period of time, this is the delay for displaying the square waveform. This is actually the code we have written for displaying the square waveform. Okay, only this is the code for displaying square. So for how much period of time we are displaying square waveform, that is decided or controlled using this for loop header. Okay, whatever you are seeing here. So same thing we are repeating for displaying the triangular waveform. These two are actually these two codes for displaying the square and triangular. We have enclosed within an infinite loop so that alternately square and triangular waveforms are displayed. Okay, so that's what we are seeing here. So for I equals to 0, I less than 1000, I plus plus, this is for controlling uh, the period of time for which triangular waveform is to be displayed. And within this two loops we are using. This is for displaying uh, these voltage levels 0 to 5 volt and then from 5 volt to 0, so that this triangular waveform is displayed. So this process you are repeating for this much duration, so that after this is completed it goes for displaying the square. So how it works is it displays square waveform, after that it goes for displaying triangular waveform. So like this alternately it keeps on displaying square and triangular waveform. Okay. So this is the fifth program of your lab syllabus. Implementation is very simple. See what and all the statements you have written in this program. Just see here. We have introduced the delay. This is the delay routine you have to write. Within the main function, you are configuring the pin select register and IO DIR1 register. So after that, you are going to write the code for displaying the square waveform, where we are displaying FFH. Yeah, this is what the digital value you are sending out, FFH and then 00H. For both, you are going to introduce the same amount of delay. And for displaying the triangular waveform, you have used increment and decrement loop. Okay, j equals to 0, j less than 255, j plus plus is the loop header you have written. And this is the statement you are repeating. IO pin 1 equals J left shifted 16 times. You know why you have to left shift J value? Since the J value will appear in the least significant 8-bit position, you want that to appear in the bit position 16 to 23. That's why you are left shifting it 16 times. And that data you are sending out or you are writing to the IO pin 1 register, which will be directly sent out to the port P1 pins. Okay. So similarly, you are writing a decrement loop, j equals to 255, j greater than 0, j minus minus, and this is the statement you have written, IO pin 1 equals j left shifted 16 times. Okay, so this is what the implementation you have to do for fifth program of your lab syllabus. Coming to the next type of question, generation of rectangular waveform. So as I told, there is no change. If you have understood how to display the square waveform, for rectangular waveform, the amount of delay you are introducing, you have to vary. So that becomes rectangular, where T on and T off will not be of same width, it will be different. So how to display it? See, this is the rectangular waveform. Either T on you have maximum delay compared to T off, or vice versa. Okay, so that it will be a rectangular waveform. Just see, so you will be at the reference voltage level 5 volts for some period of time. For some large duration compared to this T-on, for large duration you will be in the 0 volt level. With this process you are going to repeat infinitely. See what is the code we are writing. So this is the second program we are discussing. Develop an embedded C program to generate rectangular waveform using the DAC interface. We need to introduce the delay for displaying square waveform and rectangular waveform. For these two we require the delay routine. Okay, for triangular we don't require the delay routine. And here you can see we need to configure pin select register and IO dir register. So after these two are configured, next step is you'll be writing the infinite loop and what is to be repeated infinitely. That is the sending out the discrete value FFH, and after some delay we are going to sending out the discrete value 00H, but with a different delay. Just see. IO set 1 equals 0x00FF followed by that 4 zeros for sending out that is the FF the 5 volt analog voltage. Okay, then delay is introduced, delay of 10. Then we are going to write 00FF 0000 to IO clear 1 register, but with a different delay. See? In the previous case where we discussed the square waveform, the delay value was same. Whatever the delay we use for T on, same delay we had used for T off, whereas here it is different delay, so that it will be a rectangular waveform. Thus you are repeating infinitely. Return 0, close the program. See, the programs on DAC are very small and simple programs. Okay, so this is what the statements you are going to write in the main function. While 1, repeat this. Send FFH through port 1 and send 00H through port 1. So this is repeated, but delay introduced is different. Okay, so this is how we are going to display the rectangular waveform. Coming to the third waveform, generation of ramp as Sawtooth waveform. So how we can display this ramp waveform or Sawtooth waveform? Just see here, it is half of the triangular waveform. Yes or no? So for triangular, what you are doing? So starting from digital value 0 till 255, you are sending the values. After that, you had written a decrement loop, so that from 255 to 0, you are sending out the digital value. But here for ramp waveform, only this positive, that is the increment loop is sufficient. 00H to 255 if you send out. If the that process is repeated infinitely, so then that will generate the ramp waveform. Are you getting? 00H corresponds to 0 volt. Then 01, it doesn't corresponds to 1 volt. Okay, what is the digital value for 1 volt? It is 255 by 5. Okay, so what is the value you are going to get? It is 51 decimal. 51 decimal, actually it corresponds to 1 volt. That we'll discuss once we go for staircase waveform. Okay, so for the time being, just know that for displaying ramp waveform, starting from 0 digital value till 255, you're going to write an increment loop, and that value you are going to send out to port 116 to port 123, so that it displays this waveform. After that, they repeat the loop. That's all. Again, you start from 0. The voltage drops down to 0. Again, it starts displaying from 0 to 5 volts. Again, voltage drops down to 0, 0 to 5 volt. This is what the analog voltage you are generating using DAC interface. So 0 to 5, 0 to 5 is displayed, so that the waveform will be a ramp waveform or sawtooth waveform. It's a small code you are seeing here in the same slide. Programmers to develop an embedded C program to generate ramp waveform using DAC interface. So just include the header file within the main function. This is what the variable you have declared. Configure the registers, pin select and IO dir register. After that, just write the increment loop. See, for I equals to 0, I less than equal to 255, I plus plus. What is the statement you have to write? IO pin 1 equals I left shifted 16 times. Give return 0 and close the program. See how it displays this ramp waveform. I equals to 0. 0 is tested with 255. So since it is true, control enters. I value will be left shifted 16 times, and to that bits, that is 16 to 23, the data to that bit position in the IO pin 1 register. We are writing the data, and this data will be sent out to port 116 to 21. That value will be sent as input to the DAC. The corresponding analog voltage you can see on the that is CRO. Okay. So next I gets incremented to 1 less than equal to 255. Control enters the for loop and it sends out that digital value. Corresponding analog voltage you can see on the CRO. So like this, each time we are sending out a digital value and corresponding analog voltage will be generated, and that waveform we are going to see in the CRO. So once I takes the value 255, the maximum voltage, they are going to send out that value through the port 1 pins. After that, once I gets incremented to 256, it is the character data type we have taken. It will be re-initialized to 0. The counter will be re-initialized to 0. So this is actually an infinite loop what we have written. Okay, I is 0, I less than equal to 255. Once it crosses 255, I value will be re-initialized to 0. This condition will never fail. So infinitely we are displaying this ramp waveform. Okay, you need not enclose this for loop within an infinite while loop. Whatever the for loop you have written, that itself is an infinite loop. Since once I is incremented beyond 255, its value will be 0 again. Okay, so the maximum 8-bit value we can store in the character variable is 255. If we increment that, it is 0. I will be initialized to 0. Okay, so that's why this will be an infinite loop which displays the ramp waveform. So this is how we are going to display. Coming to the next type of waveform, that is staircase waveform. Let's see. This is what the output you have to display on the CRO. Just observe how many steps you are displaying. So this is 1, 2, 3, 4, 5, 6. So totally how many voltages you have to send? It is 0 volt, 1 volt, 2 volt, 3, 4 and 5. That means for having the staircase or to show the steps, you need to increment the variable by 1 volt. So 1 volt corresponds to what digital value you should be knowing. It is, just see here, 5 volts, it corresponds to 255, the digital value. So 1 volt analog value, it corresponds to 255 by 5. It is 51 in decimal, 33H in hexadecimal. Okay, so 51 decimal if you send out to the DAC interface, it is going to generate 1 volt. Okay, so remember these values. 0 volt corresponds to 0 decimal value, and 5 volt corresponds to 255, the decimal value, and 1 volt it corresponds to 51. If you want to write in hexadecimal, how to write it? So 00H digital value corresponds to 0 volt, then FFH digital value corresponds to what analog voltage, it is 5 volts, then 51 in hexadecimal it is 33H digital value, it corresponds to 1 volt. Okay, and 2.5 volt it is 127 in decimal, 7FH. 7FH, okay, it corresponds to 2.5 volts. Okay, in decimal if you want to write these digital values, it is 0, 255, and this is 51, and this is 127. 127 digital value corresponds to 2.5 analog voltage. Okay, uh, you know that for 5 volt, if it is 255 the digital value, what is the voltage, what is the digital value for 1 volt into 1? You will get 51. Okay, so you need to increment the variable value by 51 each time, so that you are going to get this staircase waveform. So first what you will do is you will send out 0 volts corresponds to 00H digital value. You send out the digital value 00H and introduce some delay. For some period of time you stay in this 0 volt line. So after that, we increment the variable value by 1 volt. 51 will add, so that it goes to 1 volt level, and you will stay in this line for some period of time. So whatever the duration you have taken for this reference line, same duration you will take. So same delay we are introducing each time. So then we'll increment the variable value by 1 volt so that it becomes 2 volt, so that this line will be displayed for some period of time. Again we'll increment by 1, it will be 3 volt value we are sending. So next increment by 1 volt, it is 4 volt value we are sending. And finally here 255 you are going to send out, so that for some period of time we will stay in this 5 volt reference line. So like this you are going to display. So after that the voltage drops down to 0. It is repeated. So this waveform is repeated infinitely. So 0 volt, 1 volt, 2, 3, 4, 5, then voltage drops down to 0. So this process you keep on repeating so that it displays the staircase waveform. Okay. So how we are handling that through the code, we'll see here. So this is the fourth program on DAC interface we are discussing. Just see here, we are introducing the delay. After that, in the main function, you know what are the initializations you have to do. So the pin select register and the IO dir register. So after this, we are going to write the infinite loop, and then this is the voltage value we are initializing in digital or in decimal. Okay, I equals to 0, and we are taking the loop. Since how many steps for the staircase from 0 to 5 volts you are going to get? It is 6 steps. So 6 times the loop I have to repeat for the staircase waveform generation. So for j equals to 0, j less than 6, j plus plus is the for loop header we have written. Within this is the statement you are writing. IO pin 1 equals I left shifted 16 times. Okay. I just you are not left shifting j value. J is for deciding the number of iterations. So since 6 steps for the staircase you are going to display, j is for keep tracking of that number of steps. But I is having the digital value which is to be converted to corresponding analog voltage. Okay. So initially, as I told, we'll be starting with 0 volt level. So what is the digital value for 0 volt you are sending? It is 0. I equals to 0. So that is left shifted 16 times and it is written to IO pin 1 register, so that the digital value corresponding to 0 volt, it is sent out through port 1.16 to port 1.23. So after that, by what amount I have to increment I? It is not I plus plus I have to do. I have to write I equals I plus 51. By 1 volt I have to increase. Okay. So that's what the updation we are doing. Don't forget to introduce the delay here. So for some period of time, it has to stay in that voltage level. For that, this is what the delay we are introducing. Then I is incremented. I is equal to I plus 51. So after that, control will go to the updation part where j is incremented to 1. 1 less than 6, condition is satisfied. Control enters. Then the new I value. So that is 1 volt. Initially I is 0. 0 plus 51 means it is 51. That is the 1 volt level. For that, whatever is the digital value that we are going to send out, which is 51, and we'll introduce the delay so that it stays in 1 volt level for some period of time. This process is repeated. Then it is incremented by 51. 51 plus 51 means that will be the digital value for 2 volts. Okay. So that value we are going to send out through port 1. So the process is repeated 6 times, and after that I is reinitialized. Since it is an infinite loop, I gets reinitialized so that the voltage drops down to 0 here. Just see, after the 6 steps are displayed, we need to repeat the loop infinitely. In that infinite loop, what is the initialization we are having? I equals to 0. Again, so 0 volt reference line is displayed for some period of time. Then we increase the I value by 51, so that 1 volt reference line is displayed for some period of time. And next 2 volts, 3 volts, 4, 5. Again, voltage drops down to 0. So the process is repeated. So this is how we are displaying the staircase waveform. Okay. So far we have discussed how to display square waveform, how actually you can display triangular waveform, how to display the ramp waveform, that is half of the triangular waveform, and how actually you are going to display the staircase waveform. The other types of waveforms you can expect is that is full rectified sine waveform, half rectified sine waveform, and sine waveform. So how to generate the full rectified sine waveform? So while discussing the DAC interface, I told how actually we are going to generate this positive cycle of the sine waveform. If you just understand how to generate the positive cycle, that we have to repeat infinitely, so that it will be full rectified sine waveform. Okay. You need to make use of the digital formula 127 sine theta plus 127 to find out the discrete values. See, this is what the program you are going to write. uh, this is the problem statement. You need to develop an embedded C program to generate full rectified sine waveform using DAC interface. Just see, in the array, we are going to initialize this discrete values. So just observe what is the maximum value, 127 till 255 you can observe. These are the values which you have computed using the digital formula 127 sine theta plus 127. The maximum voltage is 5 volt. The digital value corresponding to 5 volt is 255. Okay. So till 255 you can compute the values. After that, the same values you write in reverse order. Till pi by 2 if you just compute. So whatever the values you are seeing here, which I have underlined, it is for sampling this waveform. Okay. Till pi by 2. So same values, whatever you have computed, if you write in reverse order, that will be this part of the curve. Okay. See, 253, 251, 247. I've written the same values in reverse order till 127. So these are the total 31 values which we have initialized in this array. What you have to do is you need to pick this value and you need to send it out. Okay, and you need to perform the left shift operation, left shift by 16, so that this data appears at the bit position 16 to 23, and write it to the IO pin 1 register. That's all. Configure pin select register, IO dir1 register. After that, just see, in the infinite while loop, what we are writing for I equal to 0, I less than 31. Why it is 31 is 31 values we have initialized in the array. So 31 times we are going to repeat the loop here, and just see what is the statement we are repeating within the for loop. IO pin 1 equals data of I left shifted 16 times. Okay. Each data, this digital value, whatever we have computed, we are taking from the array and we are writing to the IO pin 1 register at bit positions P1.16 to P1.23. If you repeat this infinitely, it will be displaying only the positive cycles, full rectified sine waveform. Okay. Give return 0 and close the program. Clear? So for half rectified sine waveform, so once for some period of time, that is for 31 values what you have computed, you are displaying the positive cycle. So you are running the loop again 31 times to display this reference voltage level, which is 2.5 volt in analog voltage. Okay. In case of decimal, it is 127, or if you want the hexadecimal value, it is 7FH. Okay, 127 if you convert to hexa, it will be 7FH. So 7FH is the digital value you are going to send out 31 times, so that this half rectified sine waveform is displayed. Okay, just see how we are displaying. Initialize the same values, whatever you have computed for positive cycle, it remains the same. Whether you're displaying the sine waveform, half rectified sine waveform, or full rectified sine waveform, the for computing the discrete values for generating the positive cycle remains the same. So same 31 values we have initialized in the array. We have configured pin select register and the IO dir register. So after that, in the infinite loop, see, it is this code is same as the full rectified sine waveform code, whatever we have discussed. I equals 0, I less than 31, I plus plus, IO pin 1 equals data of I left shifted 16 times. So first 127 is taken, 127 left shifted 16 times, so that the data appears at P1.16 to P1.23. We are writing to IO pin 1 register at this position, so that this digital value, that is 2.5 volt, is the analog value that is generated for the digital value 127, and that is displayed on the CRO. Okay. So next I is incremented. Next data from the array is taken, left shifted 16 times, and it is sent out. So like this, all the 31 values what you have initialized in the memory, that is sent out to the DAC interface, so that corresponding analog voltage is displayed. So this displays the positive cycle. There's no negative half cycle here. It is rectified. You will see the reference voltage for that is the 7FH, the value. See, for I equals 0, I less than 31, I plus plus. This is what the value you are sending. 7fh. If you want, you can write 127 left shifted 16 times. Or if you want to write in hexadecimal, it is 7fh left shifted 16 times. And you are writing to IO pin 1 register. So just close the while loop, give return 0 and close the program. So this is how you are displaying half rectified sine waveform. Okay. So how to display the this is the lab syllabus program. I think you are having half rectified sine waveform for your lab syllabus. Which program you are having? Is it half rectified or sine waveform? I don't remember. I've shared the code. Is it half rectified or sine waveform? I think it is half rectified sine waveform, which is the 8th program of your lab syllabus. Okay, this is how we are going to display the half rectified sine waveform. Positive cycle. After that, there's no negative cycle. We are displaying the reference line. For that, the voltage in digital value we are sending is 127 in decimal or hexadecimal 7fh. Okay. The last type of waveform, it is sine waveform. Okay. So both positive and negative cycle you have to display, for which the rest code remains the same. Initializing the data in the array, configuring pin select register, IODIR register, all remains the same. Within the infinite loop, just see, this is what the positive cycle you are displaying. I equals 0, I less than 31, I plus plus. And this is the statement you are going to repeat. That is taking each data from the array, left shifting 16 times and writing to the IO pin 1 register. So that, and we are sending out this digital value through port 1 pins, so that it gets converted to corresponding analog voltage value. Okay. After that, how to generate the negative cycle? I just told you need to take the 2's complement. Whatever the value you have computed for positive cycle, same value you need to negate, so that you're going to get the negative cycle of the sine waveform. See, that's what we are doing. Same for loop, header we have written, and then IO pin 1 equals 1's complement plus 1. We are taking the data from the array. Okay, plus 127 you are having the first value in the array. Take 1's complement of it, add 1 to it. That means we are negating. So take the 2's complement of the values what you have computed, that you have to left shift, and loop will generate negative half cycle. Repeat it infinitely. Positive cycle, then negative cycle, positive cycle, and so on, so that it displays the sine waveform. Okay. So this is how we are going to display sine waveform. So you need to use the digital formula 127 sine theta plus 127. Using that, you are calculating the discrete values for the sampling of the sine waveform. Only till 90 if you compute, that is sufficient. Same values you are going to repeat in the reverse order, so that you get the positive cycle values. If you just negate it and if you send each value, that will be for negative cycle. Okay. Hope the programs, whatever we have discussed on DAC interface is clear. So different types of waveforms you can expect. It may be the square waveform, triangular waveform, rectangular waveform, or staircase, yeah, ramp waveform, or half rectified, full rectified, yeah, sine waveform. So these are the possible questions you can expect, or you may be given with new waveform for which you have to write the code for generating such waveform. Okay, such programs or such questions you can expect on DAC interface. Clear? Is it clear? Have you all followed?
Yes, ma'am.
Okay, we'll stop here. It's already time up. We'll stop here. We'll continue the next class.